Okay, welcome back. Let's look at laminar flows. So we just introduced equations 291 to 294, which are simplification just using the same boundary layer approximations that Ludwig-Prandtl did in 1904. So in these conservation equations, we might want to say that they're also in the literature, in aerospace literature, especially called thin layer or thin shear layer approximations. And they're applicable to wall flows like boundary layers and shear layers. And a shear layer is nothing but what comes out of, say, two flows. Like if we have two top hat flows, these are velocity vectors like this. So maybe we have u1 and u2, and u1 is much, much greater than u2. So you might have a Mach 1.5 and a Mach 0.5, difference in flow speeds, and you're going to develop a laminar turbulent shear layer. If they're very close, low Reynolds number, they'll remain laminar. There's no instability. It's Kelvin-Helmholtz instability. So a lot of these approximations apply to other flows, but we'll be talking about boundary layers especially. And these approximations are made by estimating the order of magnitude of various principal mean quantities. And these might be like quantities like U tilde, V tilde, T tilde, H tilde, etc. and P bar. These are the ones we need to focus on and do an order of magnitude analysis of these fluctuating quantities relative to these. And the fluctuating quantities you'll see in the equations like U prime squared bar, RMS velocities, U prime squared bar, other ones like rho U prime, V prime, bar, and what else? Rho, H prime, V prime, bar. Those types of quantities. So before we look at Prandtl's approximations for these turbulent flows and apply them to those equations, we're going to look at laminar flows first for boundary layers. And the first thing you'll note is a laminar flow is not a turbulent flow. So that's probably the most obvious thing. And what does it mean about all these little fluctuating quantities? They're zippo, right? They're nothing. Or if they are there, they don't grow into an instability and ruin our laminar flow. And instabilities become more instabilities, which transition to turbulence. And so even if there's a little acoustic wave that perturbs our flow, a little vibration on the surface, the flow is stable and remains laminar. So if I take 291 and 294, which are right here on this page, and I let the fluctuations go to zero, I now have something that looks a lot like the original Navier-Stokes equations again. And I've dropped all of those notations of like bars because rho bar is essentially rho. So these essentially still have these like bars on them, if you will. I just drop them because there's no point. And so now we have what? A 2D set of equations for an unsteady laminar flow, and you can certainly have unsteady laminar flow. But we will be interested in steady solutions to practice our models. So we have a mass equation, right? This is x momentum. It's written right there. Y momentum. I'm just running it again to really emphasize it. And we're going to do a total enthalpy equation. That's H. And it's still a nonlinear set of PDEs that we can't solve, unfortunately. So some quick notes about this. Remember that Prandtl's boundary layer formulation and approximations will depend on the assumptions that our gradients of quantities such as U and H across principal flow directions like X are at least an order larger than gradient along X. So this statement means that we have very little variation in turbulent boundary layers or shear layers in the axial direction or the streamwise direction of the flow. And this assumption allows us something important. It lets us neglect some of the terms in the governing equations. So there's our order of magnitude analysis. And O's are order. Sometimes I've written 0 O, excuse me. I think I tried to hit zeros in this case. Density on the order of 1. Velocity order 1. Total enthalpy order 1. Temperature on the order 1. Static enthalpy order 1. Temporal derivatives of all the terms will be on the order 1. Axial partial derivatives order 1. And radial or cross-stream derivatives will be on the order of 1 over delta. Here, once again, delta is the boundary layer thickness, right? And of course, it's small relative to length scales, like an axial length scale. So delta over L would be much, much less than 1. So let's kind of apply this order of magnitude analysis on our equations. So if we take this order of magnitude analysis and apply it to our continuity equation, which is 2.97, we'll see that the velocity components normal to the surface is order. It's going to be order delta. And so since this is small, this implies that V is small, which is good. You don't want to have large fluctuations in these types of flows. And remember, this is laminar. So what does this mean? This means U is much, much larger than V, according to the order of magnitude analysis. Let's take 2.101, the order of magnitude analysis, and apply it to the X momentum equation in 2.98, which is right here. Let's do that. What do we note? The left-hand side is going to be on the order of 1. Just looking at the time and the material derivative. Also, partial y is on the order of 1 over delta, as we noted. Therefore, partial tau xy, partial y is on the order of 1. And tau xy itself is on the order of delta. From tau xy, we can see that if it acts on viscosity, it's going to be the order of delta squared, so it's really small. And partial v partial x is small compared to partial u partial y from the continuity equation. And therefore, tau xy is on the order of mu, right? Partial u partial y. We'll leave it there. From tau xx, and mu goes as the order of delta squared, we'll see tau xx is much smaller than tau xy and is on the order of delta squared. I'm sorry, tau xx is. And most importantly, at the edge of the boundary layer, your turbulent fluctuate, or your gradients of your flow, not turbulence, excuse me, is going away, and viscous terms are very small near the edge of the boundary layer. So if we take these assumptions with the continuity equation, can be reduced to the Euler equation, and the sub E is the boundary layer edge. So this means, for example, UE is about U infinity at delta, right? So what do we see from this equation? We can kind of see that this term here is on the order of 1, which I wrote in the notes, based on this is the order of 1, an order of 1, just order of magnitude analysis. So with all these approximations here and this observation, you can rewrite the x momentum equation as 2.92. So let's look at 2.103 from 2.92. All right, there's our x momentum equation originally, using order of magnitude analysis listed here, get 2.103. Okay, now with 297, which I need to click on my notes of which 297 that was. Oops, getting lost here. 297, 102. Oh, there we go. 292. Sorry about that. Okay, 297. Let's go back, because I didn't write down on my notes. Okay, continuity equation, sorry. So this is the continuity equation. Right, 2103, which is this equation here. And once again, tau x, that's just the definition which we know earlier. So this is a simplified x momentum equation. And you'll note that there's an axial pressure gradient. And to actually do a Boussinesq solution for laminar flows, we'll have to get rid of that too. So it's still an unsolvable equation. But we're just applying Prandtl's approximations to it. Okay? All right, so next one is y momentum equation, 2.99. And left-hand side, again, is on the order of delta according to 2.101. And, well, what can we say about the y momentum equation? I note on the right-hand side, the largest stress term will be partial y of tau yy. And if you look at those terms, right, that's basically going to be like a partial u, partial y, partial u, partial y. This is on the order of delta. And if we look at other terms like partial x of tau yx, for instance, that's on the order of delta squared, which is much smaller. Partial p, partial y, if we look at the y momentum equation, is on the order of delta. So we might keep that term because there's large pressure gradient, maybe through the boundary layer. And well, that's order delta. Let me make sure I got this right. That's order delta, that's delta squared. Keep first order terms. Okay, that's okay then. So what we're going to do is reduce the pressure in the y momentum equation to be a function of x and t only and not y. And that's true a lot of times, especially like in boundary layers or jet shear layers. If I take a pitot probe, measure pressure through the turbulence or laminar flow, there's very little variation unless there's curvature in the boundary layer. So that checks out experimentally. So what does that mean? Pressure is only a function of x and t in the unsteady compressible laminar flow. The pressure gradient term in, let's see, this equation, 2.104 and 2.103, is going to become an ODE. That's pressure gradient term instead of a PDE, which is awesome. So that's our y momentum equation analysis, just applying Prandtl's assumptions for boundary layers. And of course, there's one more equation, the energy equation for total enthalpy, and which was H, right? And according to those same order of terms on the left-hand side, have the order of 1, unity. And we'll note that u tox y is much larger than u tox x y because it contains a partial y operation on u. And u is not changing much in the axial direction, but it's changing a lot in the cross-stream direction. The same for v, but v is small, right, compared to u, but it's non-zero. So since partial y goes as order of delta to the -1, right, based on units, and then partial y is got to be at the most of order 1, and qy is on the order of delta. The same can be said for temperatures, right, based on Fourier's law of heat conduction. Partial T, partial y is on the order of delta to the -1 again, and thermal conductivity coefficient K is going to be on the order of delta squared. Okay, so these are going to be small. That means Qx, partial Q, partial x, in the streamwise direction is really small. Qx, that's partial Q, partial x is on the order of delta squared. Extremely small, so it can be neglected, and that makes sense, but it's not small at all compared to Qy. Heat transfer into the flow. So if we take all these approximations, which I was noting, we can then rewrite our energy equation as 2.100. And it's a little bit simpler now, and all these terms should be on the highest order now, which is in order 1, each term, right? Not boundary order. 1 is much larger than the boundary layer thickness, unity. So we have, we still have the time and partial x, partial y terms. We still have a pressure gradient term with T. We're not making assumptions about that yet. And let's see, we have heat conduction term, and we have our viscous term again. Okay, once again, I remember now because I just looked it up out of embarrassment. This was the continuity equation, right? We use that equation and simplify. 2.107 is simplified in 2.108, a little bit simpler. And partial Q, partial y is defined this way. U tox y we're just writing out is this way. U, partial y. Okay. One observation here is at the edge of the boundary layer, the heat transfer normal to the main flow Qy and work done by viscous forces is negligible. So I'll just say it's approximately 0 at the edge of the boundary layer only. So once again, we can define a boundary condition equation, or PD, a boundary condition at the edge of the boundary layer. Remember, so this is at delta, which is at the edge, right? So that's where the boundary layer flow is laminar meets the mean flow U infinity. It's right there, right at that location. E. Okay. So what does that mean? At the edge, 2.108 would reduce to 2.109 for unsteady inviscid energy equation. And now we can use the definition of total enthalpy and introduce the Prandtl number, named after Ludwig Prandtl, mu C sub P over K. C sub P is what? Coefficient of specific heat at constant pressure, right? K is the heat conduction coefficient, Fourier, and mu is viscosity. Using partial Q, partial y again, we can write this equation here, 2.10. And we'll solve for Qy, right? It's partial Q, partial y. And then we get 2.11. So if we sum this expression for Qy and substitute it back from 2.108, which is this equation, we'll get 2.12. And this is an interesting equation for total enthalpy with this reduction in turbulent boundary layer. So we've also introduced this non-dimensional parameter Prandtl number. So usually Prandtl numbers in laminar flows goes as 0.72, and as one of my researchers, Noah, discovered recently, right, in turbulent flows, it's roughly what? Yeah, basically it's set at 0.90 in practice, or 0.99. And in laminar flows, it's relatively invariant with temperature. And unfortunately, you could imagine, like in this equation, if we set PR1, I mean 0.72 is on the order of 1, I suppose, or even if it's turbulent, 0.9 is on the order of 1, we can really simplify 2.112. But by doing that, like with a full-blown CFD solver, you would probably get wrong solutions, especially for higher speed flows. But it's interesting to just see what happens. And there's one fellow named Kroko who did this, and he derived what we call Kroko's equation, which is part of boundary layer theory, and we'll get there in just a few steps. So from equation 1.112, we'll say that it's a steady flow when PR equals 1, which is on the same order, so it's not a horrible assumption, but you'll see it's useful. Then this total enthalpy equation 112 will have a particular solution. It reduces and it has a solution. And it turns out that H, of course, is going to be constant in the particular flow if we make that assumption in a laminar steady flow. And why wouldn't it be? Because, of course, it's the total enthalpy. There's no turbulent fluctuations, it's laminar and steady, and it's compressible. And now we say, okay, if there's an adiabatic wall and the temperature is constant, then that steady state equation will have also assume zero pressure gradient. And then we can look at this equation 2.112, 2.104. This is the momentum equation we saw earlier in the enthalpy. And it'll always have a particular solution of some constant times u for PR equals 1. And so that means the temperature has to be uniform through the boundary layer, and that can be just fine at lower speed flows. That equation would have a general solution of A plus BU, which is just a linear equation last time I checked. And so if the enthalpy is the same as the enthalpy at the wall, and at the wall U equals 0, Y equals 0 from the no-slip condition, and H is also equal HE, and UHE as Y goes to infinity, you can actually match these coefficients, and you'll find this equation. So this equation, maybe I should have put it in gold or something. This is called the Kroko equation, or Kroko integral. And you see it's a compressible laminar steady flow. H is constant in the flow, and it gives a closed form solution, making all those assumptions to give us a closed form solution for H. In fact, it's like a nice algebraic equation. So this is the total enthalpy at the wall. So the enthalpy in the boundary layer is the enthalpy at the wall minus enthalpy at the wall minus enthalpy at the edge divided by the velocity of the edge times the velocity. So to me that looks like a linear type equation. It's like, you know, sort of like y equals mx plus b type equation. Because this is a constant. And so the only variable that's changing is u. U doesn't vary linearly from the wall though, right? In the laminar boundary layer, it looks more like a function like this. So we can actually decouple this enthalpy equation from our equations of motion through this closed form equation, which is cool. but it only occurs for Prandtl number 1, and it's only for zero pressure gradients, and it doesn't tell us anything about enthalpy variation in turbulent flows. But I think for high-speed flows, if you make that approximation that it's laminar and compressible, of course, steady, then you can easily estimate the enthalpy, which is a rare thing in fluid dynamics. Okay, let's see where we are. Let's start up the turbulent section, which is way more complicated because obviously we can't throw away all these correlations. So that's one wonderful thing about compressible, unsteady or steady laminar flow is we immediately got rid of all the fluctuations, all the averaging, all the correlations, all that business went away. And we even found one particular famous analytical algebraic solution for total enthalpy through a compressible boundary layer, given Prandtl number 1, which is a kind of an order of magnitude analysis. That's hard to do. We won't be able to find any wonderful result like that for turbulent flow. But what we will find is some particular useful relations between, say, like density fluctuations and velocity fluctuations, for instance. And so we're going to kind of go through the same type of procedure for turbulent flows and also talk a little bit about their physics with some graphs I pulled from some famous papers and books. So let's look at turbulent flow now. So let's look at the boundary layer approximations for turbulent flow. And of course, they would be very similar to laminar flow. So for turbulent shear flows, you'll note, just like boundary layers, well, turbulent shear layers will actually spread more rapidly than the corresponding laminar flows at the same Reynolds number. Which is an interesting physical observation. And empirically, these boundary layer approximations are also good for turbulent cases. So Prandtl's approximations are very good for turbulent flows. And I hope that's the case because his paper analyzed turbulence flows. And they're even better for higher Reynolds number flows. So low Reynolds number turbulent flows, sometimes if it's very, very low Reynolds number, close to transitional laminar flow, approximations are going to be breaking down. And these approximations aren't applied just to the variables themselves, like rho, u, v, w, p, etc. They're actually going to be applied also to the mean quantities and mean fluctuating quantities. So that's additional work for us, and it's way more complicated, as you'll see, because we're not going to make an incompressible assumption yet. So for these particular quantities, we'll use the same approximations we did for laminar flows, and the relations will be given, once again, by equation 2.101, which are from Prandtl's work. And we'll be applying them also to rho bar, u bar, etc., not only these statistical things. So the notes on the slide and my notes on my paper are a little bit different, so I got to scroll up and down. But here I want to talk about a particular figure. And before we even apply all these things to the equations, I want to try and find some relations between the statistics of these equations. So let's look at one particular figure. And I note this is the measured total temperature profiles in non-dimensional coordinates for an adiabatic compressible turbulent flow at 4 Mach numbers. So let's look at the figure. Okay. So the y-axis, I always like to describe figures because I discovered in conference as a student, I didn't know what figures people were talking about in the AIAA presentations, and I wish they would tell me, and I was too afraid to ask because I wasn't a good student at all. I was afraid to ask questions. So that was something I learned as I got older. Ask questions. So x-axis, this is y over delta, right? So this is the wall, and this is y, and there's some boundary layer with turbulence in it. Maybe the turbulence is gold, I don't know. And delta is the thickness. So that's non-dimensional. Y has the value in meters. It's the x-axis, delta's thickness. So here's the wall. And at 1, this is the edge. So this is where UE would be. Y-axis is total temperature. So we're varying total temperature, T naught, and T naught infinity. Okay, so someone, an aerospace major, want to tell me what T naught is? Yeah, stagnation or total temperature. And I mean, what is it physically? So if I have a high-speed flow, let's say I have a front of a vehicle here, and I have a little fluid parcel, as they said back in the 1800s, instead of fluid element, you would go along and you would stop and you would stagnate. And that's why they call it a stagnation temperature, and that's the temperature of stagnation. So I took this fluid particle, which is a static temperature T, like what I would measure, like we measure static temperature with thermometers. We go along, we isentropically come to rest. I would measure the total temperature. So that's your total stagnation temperature. How would I do that in a turbulent boundary layer? Well, I would have the probe. I would put the probe in the flow, and the flow comes along and it stagnates at the probe, but I would be measuring total temperature if the flow came to rise isentropically. The problem is, since I'm in a turbulent flow, flow doesn't come to rest isentropically. So these total temperatures aren't measured in the sense of like what we learn in compressible flow. This is measured with another technique, which is beyond the scope of the class. I want to talk about the physics of the measurement. And honestly, I don't completely understand how total temperature is measured in highly turbulent flows, too, to be completely honest. So I'm not going to go there. But what we're measuring basically is total temperature away from the wall, and this T naught infinity is measured out here. So that one's easy, because I can just put a probe out here, and since all this flow out here is isentropic, I can just measure that and get T naught infinity, right? So that's how we normalize it. That's constant. So what we're really getting is T is the total temperature is lower than the ambient total temperature. So this is where, right, this is the edge, if you will. I'll put it in quotes because it's not really the edge, because this is the true edge condition right here. And right here, T naught over T infinity, T naught is 1. And you can put a little line here. Okay, so you'll also note that T naught is always lower than T naught infinity through the whole boundary layer profile. So why is that? Well, you have energy losses. So if you're taking your temperature and you're deaccelerating it to the stagnation value anywhere in a turbulent flow, you have losses. So in some sense, the amount of viscous dissipation in the turbulence is somehow measured or proportional to the number of losses. So you might say, okay, here's 1. This is ideal. This is the loss. And you might say it's a loss of total enthalpy. Why? Because in ideal gas, H naught goes as what? CT naught, right? Okay. So near the wall, your viscous action's higher. And let's look at some Mach numbers. So this is ME. This is a famous paper by Morkovin and his co-worker, Finney, who I don't know anything about, but Morkovin is pretty famous in this field. This means the Mach number at the edge of the boundary layer, ME, equals 1.77. So that's 1.77 times the ambient speed of sound. That's pretty fast. So that's a supersonic turbulent boundary layer. And those are the points here. You can see right here. And so for low Mach number supersonic flows, your losses are contained in 25% of the turbulent boundary layer. Okay, so now we go higher speed. Mach edge 1.72, 356, 467 by another data set of Kistler in 1959. What's interesting about this particular set, to me, is that if I draw a line here along the 4.67 Mach number case, it comes up and it levels out here. And this is about 60% of delta. So all of a sudden, with higher and higher Mach numbers, you can see this is just below hypersonic speed, roughly, of Mach 5. Once you get to hypersonic speed and higher, then you have huge losses and temperature changes through more of your boundary layer. For low speed boundary layers, say Mach 0.1, this is almost a constant line all the way to the wall. So say Mach 0.1 here. No, well, that's supposed to be a Mach number. Let me erase that. 0.1. And indeed, this is the mean total temperature distribution along adiabatic turbulent boundary layers, really at high speed, and the measurements. And this was actually all put together in one paper in 1961. You can see this is all published after 1961. So there's some physical observations of turbulent boundary layers. So although these, although these experiments show basically that large fractions of the total temperature variation through the boundary layer occurs quite close to the wall at low speeds. So at hypersonics, our analysis, which I'm going to show, breaks down. And, okay, we got a little bit of time left. That's good. And, but generally, for high-speed boundary layers, we're going to make approximation that T naught is constant through the boundary layer. Now, if I was just doing straight up LES or CF, large eddy simulation, DNS simulation, and boundary layers, I never have to make any of these assumptions. In fact, I don't even really have to make this assumption when I'm formulating general RAND solvers. But I'm trying to formulate a simplified set of boundary layer equations that I can solve and create models for. So it's a big assumption. As you can see, by making that assumption, just at Mach, say 1.5, 20% of my layer doesn't have a constant T naught. But just also look at the scale, just so you know. This is really 0.94, so there's only a 5% variation below Mach 5. Right, so you can see we're about a 1% deviation from T naught constant for Mach 1.5 roughly. So it's not that bad of an approximation even for supersonic turbulent flow. But it's not, it's an approximation. Okay. So with that, I can always write, in my definition of total enthalpy is static enthalpy plus the kinetic energy. I can write out my time average enthalpy, plug in this definition here, and expand. And I'll get this right-hand side of my unnumbered equation. And then I can define, by looking in here, I have an h bar, and I have 1/2 u bar squared. This is a mean total enthalpy, which I'll call h bar. And I also have the other components. I have a double prime, I have a u bar double prime, and I have a 1/2 u double prime squared. I'll call that the fluctuating total enthalpy. So that's just done by taking the definition of total enthalpy and substituting in basically my time average and fluctuation term for h and u. Okay. So I've done that. And I'd like to note that experiments done by people like Morkovin in the 50s have shown that for adiabatic turbulent flow, the total temperature or total enthalpy is constant, which I've already noted, but therefore the total fluctuations must be small, especially because it's about the mean, because these are really mean measurements. They're not taking fluctuating measurements. You can't measure the fluctuating temperature about a mass average temperature or average temperature. So that's very difficult to do, and I don't know anybody doing it. Maybe even today. I could be wrong, be happily wrong. But this will be one observation based on this graph. And so we can say h double prime is equal to the rest of our definition from 2.115. We'll just say that's approximately 0. And that's a really good approximation that we can use to reduce our equations based on measurement. We can also say, because they're small, like u double prime squared is on the order of 2, second order. The above expression will be small compared to u bar u double prime. It can be neglected. We'll also say that C sub p, coefficient of specific heat at constant pressure, right, is going to be small. And then the resulting expression for enthalpy can be rewritten as temperature. T double prime over T bar will go as negative gamma minus 1 m bar squared u double prime over u bar. So this is how we're going to define local Mach number in the boundary layer, right? So C bar equals the square root of gamma r T bar. And that's where that came in that equation, right? Because m equals u bar over C bar, right? The speed, the local velocity divided by the local speed of sound. So that's what that term is in this equation. Okay, there's some experiments first done by someone named Kistler, and they were in 1959. Took measurements of boundary layers in wakes, and they found that H double prime is goes about 0.2. It's very small. So to illustrate this, I want to show figure 2.3, which will show distributions of total temperature fluctuations at 3 Mach numbers. So let's look at figure 3. It's way down here in my LaTeX. So distribution of total temperature fluctuations according to Kistler for adiabatic walls. Same type of coordinates. We have y over delta here. This is called outer coordinates. We'll talk about inner coordinates. Well, I think we've already talked about inner coordinates. So here's the edge, and here's the wall. And once again, we have T naught and T prime squared bar square root. What is that? RMS, root mean square temperature, right? So we take the square, we take the mean, and the root. So this is T RMS. If we didn't do it in that order, we would just have T, the variable would be 0 if we didn't do it in that order, right? So we have RMS temperature normalized by the stagnation temperature as a distance to the wall. Here's 3 Mach numbers, 172, 356, 467, all supersonic, highly turbulent flows. None are hypersonic. We're not going to do hypersonics. You can see the highest levels of T prime or TRMS are here. So this is what? M equals 4.67. 3.56, 1.72. So you can see at Mach 1, you're on the order of 1% TRMS, which is negligible. Okay, so we're almost done today. We'll just kind of finish up some of these thoughts and get to a break. So we see that the maximum total temperature fluctuation is less than 5% at the highest Mach number, which in engineering is negligible. And we see that our equation, 2.117, is for adiabatic flow. And by using the Croco integral, one second, let me finish this thought. You can see that for heat transfer at the surface of the boundary layer, and it's turbulent, will go as this. So we're imposing the laminar boundary layer solution near the wall based on Croco's integral. And it has the same linear solution. So in the laminar case, this was just U, and we replaced it by U bar plus U double prime, which is like a Rand's average. And we expand B on it. So I had a question here.
How chaotic is this nonlinear set going to be? Because you said that less than 5% was going to be negligible, and I do think that's like true. But when, like in the project, we altered it by a factor of 10 to the minus 4, which is way less than 5%.
Yeah, good question. So let me repeat the question so I understand, make sure I understand your question. So in the computer project, we were studying chaos theory where we basically perturb initial conditions to see what happens to solutions a long time later. And in this case, I'm basically, for the sake of analysis, making big assumptions in terms of like numerics today, where I say, okay, well, the temperature fluctuations in the boundary layer are only up on the highest 5% at the onset of hypersonics, and probably less than 1% for the lowest speed flows. In fact, the temperature fluctuations are nothing for very low speed flows. So the question is like, how can we get away with this? And I guess it's a little bit unsatisfactory because, when these assumptions were made, people didn't really have digital computers at all. They're laying out these equations and trying to create a boundary layer set of equations. So 5% temperature fluctuations is huge. And in the real set of nonlinear equations, if you perturb your temperature fluctuations by 5%, I'm certainly sure that the evolution of that turbulent boundary layer is going to be huge later on, like almost immediately, because you're basically changing solution in the energy equation, especially right away. And so you would see immediate changes in all the turbulence, because it is highly chaotic, nonlinear, like you say. But to get at a set of equations which you can close with simple turbulence models and make practical predictions, you'll have to make some assumptions for the sake of analysis. So that's why I'm making some of these physical observations to try and reduce this set of general equations to something that we can close and model with simple equations.
So if you
And one more thought is when we get to the end of all this and just see the simplest models, which are algebraic, you'll see that they're incredibly predictive, that your error will be on the order of 1%. And also this is for statistics, right? So the computer project, we were looking at chaos theory. That's a completely deterministic thing. We're trying to find the exact flow field at any time. And the statistical methods, we're trying to predict the statistics of turbulence. And we can predict the statistics of highly turbulent flow, but we probably cannot predict exactly the deterministic temporal evolution and compare that one-to-one with a measurement, ever. Even by taking a measurement, we send a perturbation through the whole flow, which changes everything. It's just like any other measurement theory. If you measure something, you change it. So that's kind of a long explanation. I'm not sure if it's completely satisfactory, but it's probably where we are in the field. Yeah. Does that answer your question, or maybe I misaligned it? Yeah, and it's a great question. And I mean, in the interest of time, and I know this is really difficult material to understand, we'll probably take a break here and come back Thursday with fresh eyes and think about some of the things we talked about, especially Morkovin's measurements of temperature and how it relates to chaos theory. We can discuss that too. So thank you so much for your time today, and we'll see you Thursday.